Hello everyone. Our research project is called a new longitudinal error balancing approach for closed traverses, mathematical model. Author Lionel Ramírez Durán, co-author José Ligüen Manzano. Faculty mentors Dr. Gustavo Maldonado and Dr. Marcel Majiar. While plotting a closed traverse, the endpoint coincides exactly with the provided starting point. This means that the algebraic sum of the latitudes, the sum of the northing minus the sum of the southing, should equal 0. In the same fashion, the algebraic sum of the departures, the sum of the eastings minus the sum of the westings, should also equal 0. However, due to errors in field measurements of angles and distances, the calculated traverse might not close on the starting point. The distance by which the endpoint of a survey fails to meet with the starting one is called the closing error or error of closure. An existing classical error balancing approach developed by the American mathematician Nathaniel Bowditch in 1807 is widely employed in polygonal closed traverses to balance or correct longitudinal errors of closure by stretching or shortening all polygon sides by amounts proportional to their measured length. Although this existing error balancing approach does not properly correct the actual error of closure because it assumes that all sides of the polygon are erroneous. This study presents an alternative approach to balance error of closure via sensitivity analysis based on a small variation of the length of all involved sides. In the first place, we start defining the variable for an n-side traverse, where E is the error of closure, L sub I is the length of the side I, and P is the perimeter of the traverse. The longitudinal error precision epsilon is defined as the quotient of the error of closure over the perimeter. Correspondingly, the denominator Y is defined as the perimeter over error of closure. That is, the longitudinal precision epsilon is 1 over Y. This is an iterative method that starts writing the denominator Y as a function of the length L sub I, letting one length L sub I variable while the remaining ones are fixed. The function Y L sub I is plot versus L sub I, and the partial derivative of the function Y with respect to L sub I is determined. Then this partial derivative is plotted against L sub I. From this graph, we can analyze that when with the partial derivative of Y with respect to L sub I is 0, the maximum value of Y is attained. The proposed error balancing approach reduces the longitudinal error and effectively closes the traverse. This research is still in progress, and its effectiveness will be corroborated by accurately measuring a field traverse using a global navigation satellite system device during 4 continuous hours at each traverse vertex. The proposed novel methodology could be highly applicable at surveying geomatics institutions such as the Surveying and Mapping Society of Georgia or the Georgia Department of Transportation. Thank you. I think it went right.